Ever wonder if you could build a fully functional Linux system from Windows? I did, and I didn't mean by using the Linux subsystem for Windows, since that would be cheating, and I have something far more cursed in mind. Right now, you're watching Windows XP installing in what was a 4-hour session to simply get this project to the starting line. We're going to be doing this with Services for Unix, or SFU, which was Microsoft's follow-up to the POSIX subsystem, which essentially existed to make Microsoft eligible for government contracts and was essentially unusable for purpose. SFU, meanwhile, is something you might be able to use. It implements enough Unix compatibility that you can run programs that require a C library with more than 110 functions. If you want the gory details on the POSIX subsystem, I have a full video on it, but watching that one isn't necessary for this one. Now, dear viewer, you're experiencing this video in essentially real time with me, since at the time of recording this segment, I still don't even know if this is possible, and I don't intend to re-edit this video like I usually do. You're going to get my thoughts and conclusions ran immediately after and pieced together from each stream, and watch this train wreck in real time. Normally, I do my projects off stream, edit them together, and ship them. This has led me to finish several projects and then get halfway through the editing and burning out. I'm going to talk more about the behind the scenes things at the end of this video and some coming changes to the channel, but for now, Subsystem for Unix. SFU was actually originally a third-party product known as OpenNT and then InterX, which did what Microsoft didn't and create a usable Unix-like environment on top of the kernel. Microsoft promptly bought the company who made it and shipped it in the form of Subsystem for Unix. Versions of SFU existed for NT4, 2000, XP, Vista, and 7 before it was replaced with the Windows subsystem for Linux version 1 and then the current Hyper-V based WSL v2. I don't know how much SFU was used in practice, but it included things like an actual usable shell, a port of GCC, and even a full set of X11 libraries. So you can conceivably use it to port software from a Unix host and then run it on top of the NT kernel with relatively little effort. This isn't a virtualization or emulation solution either. Like the original POSIX subsystem, this is a Unix-like environment running directly on the NT kernel. However, all this is academic if I can't actually get it running, and this is why my first stream was 4 hours of getting XP to behave and then dealing with even more unexpected breakage. Originally, I was going to do this in VirtualBox since it typically works way better for older operating systems, but that would require it to be faster than a Glacier. This is also why, despite having this idea half a year ago, I was stuck waiting until I had my desktop system, known as Absolution, back with me. Doing this in UTM on a MacBook Pro would just suck. The problem here is that Windows 11 essentially requires Hyper-V to be enabled for things like WSL, security features, and a lot more to work. When Hyper-V is enabled, VirtualBox can only run in a very slow emulation mode that's probably about the speed of a mid-90s Cyrix processor. You can disable Hyper-V with BCD Edit, but it breaks about half of Windows 11 when you do so. So after waiting about an hour for XP to install in VirtualBox and some urging from the stream, I went to work to getting XP running on Hyper-V. This sucked. XP isn't officially supported on modern versions of Hyper-V, but you can kinda get it to work by using the first generation option, installing from a disk that has Service Pack 3 slipstreamed in, and then manually installing an older copy of the Hyper-V guest editions from Windows 7 into the VM. You also have to use the legacy network adapters in your system configuration, or your network will only appear to work. Thank you to the Nico2 for helping me figuring out all the steps necessary to get this to work. If you do all that correctly and cross your fingers, XP will boot up under Windows 11's Hyper-V, and then it is possible to use remote desktop connection to get it to scale properly on a 1080p display. That only took 2 hours to accomplish. From this point, installing Services for Unix is trivial. Stick the CD in the drive, run the setup program, and then just make sure to install all the optional components. After that, you get 2 new options in the start menu for a C shell and the Korn shell. And when they say Korn shell, they do mean the original 1988 release, not the newer KSH 93. For reasons entirely unknown to me, Services for Unix ships what can be best described as, even by the standards of 2003, an antiquated userland. If Wikipedia is to be believed, These tools were sourced from OpenBSD originally. Its make utility is so old that NetHack failed to build. Oof. That isn't such a big deal since Services for Unix does ship with a copy of GCC 3.3, which unlike everything else was roughly current when SFU for XP was released. Furthermore, if I was going to have a serious try to cross-compile Linux under this environment, I was going to have to build a lot of support software to begin with. So, after figuring out a way to punt files into the XP VM, I grabbed a copy of GNU Make and Bash. Make to replace the pathetic system make utility, and Bash since I prefer my shell environments to be at least slightly younger than I am. This is where I discovered that GCC was broken. When building GNU Make, configure fell over saying that the C compiler was broken, and I quickly realized that GCC was segfaulting, or more specifically CC1, a backend component. Some testing revealed that while CC1 would crash if invoked by GCC, it would work if I invoked it directly. Lovely. Also, GDB would crash whenever I tried to debug the crash, so I'm once again stuck in a case where I need to debug the debugger. This felt like an omen of things to come. 2 hours of going around in circles promptly followed. It was at this point a viewer in chat, HTF Crino 2000, brought up the possibility that Windows XP's Data Execution Protection, or DEP, might be breaking things. DEP is Microsoft's fancy name for a processor feature known as NX, or no execute, and it's a security feature to prevent certain code bugs from being a security exploit. XP will use the NX feature on Intel-compatible processors if it is present. NX wasn't super common when XP released, but my 2020 AMD Ryzen has it, and thus XP was using it. XP by default only uses DEP on certain critical system components, but as subsystem for Unix directly talks to the NT kernel, so it might be affected. As such, disabling DEP seemed like it was worth trying. Fully disabling DEP isn't straightforward since it requires adding boot.ini to change the no execute option to always off. Shockingly, after doing this, GCC started working. Some Googling did reveal that this is an actual bug in SFU and that there was a hotfix that fixed it. However, said hotfix is almost certainly lost to time, but no matter. Huzzah! We have finally reached the starting point of this project. It was at this point that the wet string that represents my internet connection broke, so I ended the stream there, copied my video files to my NAS, and punched out this script, wondering where this project was going to take me next. Striking while the iron was hot, I started day 2 right where I left off, deep in subsystem for Unix and seeing what I could do with it. With the GCC problem solved at the end of last stream, it seemed like the sky was the limit. I still wanted to get NetHack built as a Sandy test, so I kicked off the session with trying to get GNU Make built. Make is a build utility. It reads a file known as a makefile, which contains a set of directions on how to build a given utility. Unlike before, configure ran to completion, but the build itself fell over. Some examination of the build failure seemed to be due to a missing file. This actually seems to be a packaging problem with a copy of Make I grabbed and a slightly older version built without issue. It was a weird start to the stream, but as I was about to find out, it was a sign of things to come. With a newly built Gmake, I was able to build NetHack, and some brief testing showed that it worked. While I'm always down to hunt the Amulet of Yender, I had bigger fish to fry. However, the road ahead was difficult and fraught with danger. To actually pull this off, I was going to need a piece of software known as a cross-compiler. As you may or may not know, computer programs are written in programming languages such as C. Compilers like GCC turn that human-readable source code into something your computer can run. Cross-compilers do that, but they build the code for a different machine than what originally built it. By building an InterX to a Linux cross-compiler, I could cross-compile all the programs I need to make a minimal but functional Linux system from scratch. Cross-compilation on paper is straightforward and is the standard method of developing things like iOS and Android apps. However, in practice, cross-compilation often ends up being painful in the best of times, as we will no doubt see. Fortunately, GCC can be reconfigured to operate as a cross-compiler. This would require rebuilding it from source with the -- target flag, which would tell it what platform to build code for. Here's where we get to the first hurdle. Microsoft had shipped GCC 3.3 with services for UNIX. GCC has supported cross-compilers since at least the 2.x days, but I knew from experience it was quite fiddly to get the older versions to actually build as a cross-compiler. Ideally, I wanted to be on GCC 4 at a minimum, since GCC had largely cleaned up their build system at that point, and it would simplify everything else. I also figured that this wouldn't be a problem. However, I couldn't just build a GCC 4 based cross-compiler straight out of the gate. When being built as a cross-compiler, GCC needs to be built with itself. Not only that, but the host compiler needs to be relatively close to the version of GCC being built. In short, I need to build GCC 4 for InterX first, and then and only then could I build a cross-compiler out of it. When starting up the second stream, I thought I could punch this out in a few hours and call it good, but it wasn't quite so easy. Before that though, I wanted some quality of life. As I stated previously, services for UNIX was a fairly minimal environment, and most of the utilities it did had were fairly old versions ported from OpenBSD. There were quite a few collections of precompiled tools floating around on the internet, but in the spirit of this project, I wanted to do it myself from scratch. At a minimum, I wanted Bash as well as some support utilities like an updated grep. Building these were all relatively straightforward, although it took a few tries to find versions that would actually build. It's through this process I learned that SFU lacks wide character support. This isn't really that surprising, as wide character functions weren't standardized until POSIX's 2008 edition, but it did let me know the upper range of what I could and couldn't expect to build. That hiccup aside, I was able to build Bash 4.4 shortly thereafter, and that gave me tab completion, which is a very nice quality of life improvement. grep quickly followed, although I couldn't get tar to build despite trying a few different versions. Still, the system tar, while a bit clunky, was good enough for now. With that, I had a slightly less threadbare environment and turned my sights towards GCC 4. GCC, or at least the versions made around the mid-2000s, require 3 support libraries to be installed and made available. These are the GMP, MPFR, and MPC libraries. These libraries have functions for handling large numbers and floating point numbers and are a hard dependency for GCC. I started with a copy of GMP 5.1, and at first things seemed well. GMP built without issue, but when I ran make check, I got test failures. And it wasn't just one failure, it was a bunch of them, with the ominous message of Windows NT exception, suggesting that something fundamental was broken. Between the first stream and the second, the Nico 2 had managed to find a bunch of hotfixes for services for UNIX, as well as some knowledge base issues suggesting the problem was with Microsoft's copy of GCC or the subsystem itself. Unfortunately, installing these hotfixes didn't do anything to solve it. However, I had a few ideas. For performance reasons, GMP uses a lot of hand-written floating point assembly code for different machine families. There's also a generic C version that can be enabled if all else fails. I theorized that perhaps services for UNIX didn't like how GMP's hand-ran assembly code worked. Along these lines, I forced it to use the 486 version of the code, as this would limit it to the 8087 floating point instruction set. It was a great idea that didn't make a lick of difference. Great. What about the generic version? Nope, still more test failures. While I do have a copy of GDB, it was still continuing to be useless in the face of everything. It couldn't read core files, and it didn't give any useful information when attached to the test binaries directly. At this point, I was getting concerned that I wasn't actually going to be able to build GCC 4, since my attempt to build MPFR, the second library in the series, also had test failures relating to many math functions. I knew these were due to the earlier GMP test failures compounding upon themselves, and at this point I knew if I didn't solve this, I might be dead in my tracks. I did come up with a backup plan, but I wasn't quite ready to give up on having GCC 4 just yet. I found some bug reports that had patches that allowed GCC 4.2 to build for InterX, and officially GCC 4.6 was the latest version that still officially supported the XP era of services for UNIX. So there was some hope, but I had to solve this GMP problem first. At this point, I'd been streaming for about 5 hours, and I was starting to feel fatigued, But before I shut down for the night, I decided to try a version of GMP from about 2008. I'll be honest, I wasn't optimistic about this working. When building the earlier version of GMP, I had intended to build it as a generic C-only version to give this the best chance of success, but I was so tired at this point that I flubbed the configure line and accidentally built the version with handwritten Pentium assembly. Regardless, I carried on and watched Make slowly grind through the build process. After it finished, I ran make check and waited. Much to my surprise, it worked. No test failures. I really wanted to end the stream now, but I also decided to rebuild MPFR to see if those issues went away, and they did. Sorta. I still got some test failures, but as opposed to the lines of red I got earlier, this was a much needed improvement. At this point, I was approaching the 6-hour mark, and I'd figured I'd get back to it after a good night's rest, so I ended the stream with some reason to hope that this was actually possible. The third session of this project started a few days later, over Easter weekend. I was well rested and hoped that we'd make some good headway today. At this point, I had crossed the first hurdle of getting GMP and MPFR built and moved right on to getting MPC built. However, that crashed into a brick wall as MPC fell over during configure with an error telling me that my version of GMP was too old. That was a great start. So right back to GMP I went. I went with the oldest version that would also satisfy MPC, which was 4.3.2. I was worried I was going to end up right back where I started, but nope, it built just fine and its tests passed without issue. Huzzah! We have now found the Goldilocks zone of GMP versioning. Next was actually tackling the main meat and potatoes for this stream, GCC, and that started with extracting the tar archive from ftp.gnu.org. As you can probably guess given the fact that I'm bringing it up, this process failed. The system tar couldn't deal with GCC's long paths and died. However, this failure mode was not entirely unexpected. I have run into this problem with various non-GNU versions of tar in the past, so to get around this issue I needed to get GNU tar built and working, and having learned my lesson on trying to build new software, I grabbed version 1.22. Unlike my last two attempts, this built without issue. After installing it as gtar, I was able to extract GCC 4.6 without issue. Now, I should note I intend to build the last version of GCC 4.6, which is 4.6.4, but I accidentally downloaded 4.6.3 and didn't notice until several hours later. Oh well. Now came tangling with the beast. I knew from the GCC bug reports that I had read that to get anywhere with this, I was going to have to do some patching here. I was also going to need to update a few utilities. First among them was sed. Sed is a streaming text editor for doing search and replace, and apparently during GCC's build process, the system's sed chokes on large files. No problem. I first built GNU sed 5.2, but this version had some problems. It kept complaining about flushing std in, and quickly led to quite a few other things breaking. However, downgrading to sed 5.1 seemed to resolve it, and all tests passed. With that little pain point resolved, I applied the patch I had for GCC 4.2 to 4.6. As expected, several parts of the patch failed to apply, although it wasn't terribly difficult to fix the rest by hand. Now, there was nothing to do but configure and attempt building. Unlike other parts of this project, configuring GCC requires a lot of switches. In short, we're telling GCC to build the C and C++ frontend, the threading model, to disable internationalization, as well as the locations of GMP, MPFR, and MPC that we built earlier, as well as enable obsolete, since at this point in GCC's life, the Interix target was about to be removed. Configure ran without issue, and thus started the very long and very slow make process. And this was slow. Very slow. Make would stall for minutes on end between various build steps. Looking at it with Process Explorer, it seemed to be checking every single file in GCC directly. We're now seeing the first-hand reason like tools like Ninja were ran. Making it even worse is the fact that services for UNIX kinda sucks for I/O. I had noticed that file access had seemed laggy prior to this point, but this was when I was really starting to feel it. The practical end result of this is that it took about 10 minutes of processing time before anything would start building, and I had to wait for this processing step every time I had to restart the build due to a build failure. I ended up watching the process in Task Manager and watching the memory usage go up in an effort to judge how far Gmake's process was at enumerating files. I also knew that this delay was going to get much, much worse. When GCC is native compiled, it does so in 3 build stages. The first stage is building a minimum version of GCC known as XGCC using the system's native compiler. XGCC is then used to build the rest of the compiler. In stage 2, creating a fully functional XGCC with all the options we set. Stage 3 then rebuilds GCC with the just finished XGCC as a sanity check, as well as building a few additional components such as the C++ standard library. That meant, at a minimum, I was going to have upwards of an hour of just waiting for make to slowly trawl directory trees, and that was making the assumption there were no build failures. Spoiler alert, there was. Adding insult to injury is that when running with the J option to enable parallelized builds, Gmake would occasionally deadlock, forcing me to restart the build all over again. This problem, combined with the previous one, was actually bad enough that I gave up trying to parallelize make at all, since any time I saved from parallelizing compiler tasks was immediately lost in all the time it took for Gmake to catch up from a hung build. So that gives you an idea of what I was working with. Now we need to talk about the slew of errors I ran into trying to get GCC 4.6 to build. The first build failure actually came from Windows XP mysteriously crashing. The VM had automatically rebooted, and I had stepped away from my desk for a moment when it happened, so I didn't see anything on the console either. According to the Hyper-V event log, the XP VM had triple faulted, which tells me something bad happened and no other useful information. There was quite literally nothing I could do about this one but continue and hope XP stayed stable through the torture test I was putting it through. The first real build failure came shortly thereafter from an awk script breaking with a syntax error. From what I could tell from the build messages, GCC's build process was trying to run an awk script to generate configuration headers for the CPU platform and host operating system. Normally, these errors are caused by the awk interpreter, which in this case is Gawk, being too old. But much to my surprise, Services for Unix actually had version 2.15.2 pre-installed, which was up to date with approximately 2009. I guess one of the hotfixes I installed must have upgraded it, but that left me at a loss as to what had actually broken. An examination of the awk script showed that it was trying to run a function that had been commented out except for the opening and closing brackets. I added a dummy variable to it to make Gawk happy, and running it by hand showed that it was properly generating compiler definitions afterward. That was a quick and easy fix. Less easy was the next build failure that followed. The build died due to a missing variable declaration. Internally, GCC's Interix backend shares code with both Cygwin and MIG-W for building on Windows targets, and those backends had to add some options that weren't defined for Interix. After staring at the backend code for about half an hour, I wrote a quick patch and we were on our way once again. I kinda expected it to be a bit rot, but the next failure caught me off guard. The assembler started crashing. As part of the build process, GCC runs multiple configure scripts recursively to, well, configure itself. When trying to configure XGCC, the build system was testing what options that Microsoft's assembler and linker supported. Under the hood, Microsoft had shipped patched copies of GNU bin utilities to provide an assembler and linker for Services for Unix, but it seemed whatever changes they made didn't play well with GCC's configured script and the assembler tapped out. The fix for this one was also fairly easy. Download Notepad++, open the configure script, and hardcode the test to say, "No, my assembler doesn't support this feature." After kicking off the build again, I quickly ended up with XGCC successfully built. That meant I had the core of GCC 4.6.3 building. However, a few build steps later, I quickly found out that my newly built XGCC was broken. It couldn't even build an object file, let alone a binary. The problem here was due to CC1 again, although unlike before, it wasn't a data execution policy problem. It was due to the fact that CC1 couldn't locate libmpc.so.3. That's a little bit surprising, although in hindsight it makes sense. Normally on Linux, a feature called rpath is used to prevent having to set manual library paths like this. However, at the end of the day, services for Unix applications are Windows applications, and Windows doesn't have an equivalent feature to RPaths in its portable executable format. Some testing showed that I could add opt_tools_lib to LD library path to get it to find MPC. This was an easy enough fix, although I still couldn't actually build hello.c. The reason is libgcc, which is a compiler support library, was still missing, since it had yet to be compiled. Kicking off the main build again died though shortly thereafter. The build failure this time was due to a bunch of assembler errors trying to build sigwin.asm. A review of the code in question showed that it was trying to use an assembly feature known as CFI, or call frame interface. The technical bits here are a little too complex to get into, but the short version is that configure does a check to see if the assembler supports CFI. Configure did properly detect that our host assembler doesn't support CFI, so this flag shouldn't be set. The problem here is that instead of undefining the CFI macro, configure defines said macro with a value of 0. The proper way to fix this would be changing the AutoTools macros to properly undefine the CFI flag, but that would require getting all the AutoTools development packages working and then running autoreconf. I instead changed the if-then statement in sigwin.asm instead of torturing myself with M4 macros. With that done, libgcc built and I was able to use xgcc to build a hello world binary without issue. This is probably the first time GCC 4.6 had ever been used on InterX for XP, and it was a major victory in and of itself. I wasn't quite out of the woods just yet. Going back to the main build after crossing this milestone, the next problem quickly emerged. The build exploded trying to build the C++ compiler due to a missing file on the linker command line. The file in question was ci3a6.0, which was built but wasn't properly being referenced in the make file. I worked around this one by running the link command manually with the missing file added. Sometime later, I did actually find the root cause of this issue, which was due to a sloppy edit that either I or the earlier patches made on config.gcc. At this point, I had been streaming for 11 hours though, and I was spent both mentally and physically. So with the build still running, I shut the stream down and resolved to get back to it the following day. Little did I know that there was one major hurdle left to cover. When I got back to the build the following evening, I saw that it failed building the C++ standard library. However, this build failure was different. It was failing due to a missing header, student.h. Also, I forgot to hit record while debugging this, so you're watching the small amount of footage I did record on what would be my 4th live stream in this series. Student is actually supposed to be part of the System C library and it provides several useful variable types like uint16. It's part of the C99 standard, which, as the name suggests, was standardized in 1999. Microsoft, meanwhile, rather famously, didn't comply with C99 until the release of Visual C++ 2015, nor did they support C99 under services for Unix either. Earlier versions of GCC, such as the known-to-work GCC 4.2, didn't have a hard C99 dependency, so the question now was, had I come so far just to meet failure? Of course not. Now, I'll be honest, I must have had some amazing sleep the night before because I had this figured out in about 30 minutes. GCC actually has a mechanism to generate these missing header files, and they're already used for the 2 other Windows targets, Sigwin and MingG. This is a good time to briefly talk about those. MingG is essentially a basic port of GCC to Windows with a few support functions front-end that let GCC, Bash, and a few other programs basically just work. It generates standard Win32 programs, and just like standard Windows programs, it has no good way to enable case-sensitive file system operations, so I can't use it to build Linux. Sigwin is, on the other hand, essentially a POSIX library on top of Windows and was probably the most common way to run Linux and Unix software on Windows. There are ways to make Sigwin support case-sensitive file system operations, but I decided to use services for Unix instead simply because I was interested in trying it out. What's important here is that both MingW and Sigwin uses GCC's internal mechanism to provide a copy of stdint.h that would theoretically allow GCC 4.6 to work on InterX. I was fairly certain the variable sizes would be the same since, as I stated before, subsystems for Unix applications are Windows applications, just not ones that use the Win32 API. Ultimately, what this boiled down to was going through config.gcc, adding a couple of lines that told it to create stdint.h, and then use the mingw template to generate it. The downside to this is I would have to restart the build from scratch. So that's what I did. The rest of Stream 4 was building GCC and keeping an eye on it. There was really nothing to talk about since I had already covered all the important stuff last time, so I ended up grinding an agility level in old school RuneScape, as well as completing Jagex's Easter event. The question though was, did it work? Well, sort of. Halfway through the build, I checked in a new terminal that stdint had in fact been generated, showing that my patches had worked. However, the build actually errored out again in the same place, talking about stdint. I think in hindsight, what I needed to do was just build GCC with only the C compiler and then rebuild it with C++ support, so the header would be properly installed and referenced, but that didn't occur to me at the time. What I ended up doing was fishing the header out, putting it in user include, and then continuing the build. This got past the first failure and then immediately died with a second failure on conflicting types. Going back to the build the C compiler first, GCC actually does a lot of post-processing on its headers during the install process, known as fix includes. I suspect that needed to be run here, but instead I just manually massaged the file by commenting out the conflicting definitions to get past the build error, which then died 3 seconds later with yet another failure, this time relating to the entries I had just commented out. So I uncommented them again, and with that the C++ standard library built. Nice. I ended the stream there as I was starting to fall asleep at the keyboard. The following morning, with a bit more hand-holding, gmake bootstrap ran to completion, and I ended up with a fully built GCC 4.6.3 for InterX. Now the question was, would it work? That was the topic of my next stream. Well, this is where I was going to run the GCC test suite, but I failed. But not for the reasons you might think of. This isn't GG for the project, but it was proving how difficult this project was going to take to the finish line. The problem here is that unlike all the other tests run up to this point, GCC's test suite requires some additional software, namely the tool command language, or TCL, and expect. I spent about 10 hours trying to debug this on stream and even more time offline, and I got basically nowhere. Furthermore, unlike GCC, strictly speaking, running the test suite is optional, and thus I could squeak by without it. It's not a good idea, but I could spend weeks staring at TCL and getting nowhere with it. The VODs are up for anyone who wants to see the whole thing, but the short version is that TCL never officially supported InterX. I did get TCL 8.6 sort of working, although it required a lot of patching to get there, and even then failed a lot of its internal tests. Even after getting TCL working, expect died with multiple problems relating to pseudo TTYs, and then it started seg faulting deep within the TCL core library. Now, if I had a working debugger, I might have been able to fix this. I did get some debug information out of GDB for a change of pace, but I quickly realized that it seemed to be returning garbage data out, as the functions it reported we were in seemed unrelated to where I knew we were in the code. I had built these with my new and shiny GCC 4.6 compiler, so you might think that this was a problem with my Magnus Opus on XP, but you'd be wrong. When built with a Microsoft-supplied GCC 3.3, TCL died, complaining that it doesn't support decimal computers. You know, the type of computer that works in base 10 instead of base 2, so that's fun. Also, since people kept bringing it up, WinDebug or debugging tools for Windows wouldn't help me here. While services for Unix applications are Windows applications, they're built by GCC, and Microsoft's debugging tools do not understand GCC's debugging format. That means I'd have to work without symbols and essentially use tools like adder to line to convert memory hex addresses to code locations. I'd prefer not to do that if I can avoid it. It's an option available as a last resort, but I'm not that desperate yet. What's frustrating about this is that there were versions of TCL that did work on services for Unix that have disappeared off the face of the internet. Furthermore, Package Source, a package collection maintained by NetBSD, also at one point both supported InterX and TCL on InterX. The problem here is that while old versions of Package Source have survived, they need a collection of old source bundles known as dist files to successfully build. Just to bootstrap package source, I'd likely have to track down at least a dozen very specific versions of old utilities, and then probably a few dozen more just for a chance to build Tickle successfully. It's not impossible, but I wasn't optimistic that package source's Tickle was any more functional than mine. I did try taking their patches for Tickle 8.4 and building it by hand, but to no avail. I do know from experience that package source does a lot of manipulation to the build environment and replaces almost all tools with their own custom patch versions, so short of spending would likely be a week hunting down all the source packages needed to build package source and hoping it would work. I called it. I don't need this to progress, but I was kind of counting on it to both run the native compilers test suite and the cross compilers to know that I was actually getting good compiler output. That said, this session wasn't an entire loss. While discussing the problems and going around circles, and labs plus a few other viewers in chat were curious as to why my build of GCC could build Tickle at all while Microsoft's GCCs failed. What we found is that InterX actually has a broken math function known as frexp. Under GCC 3.3, this function is called like any other and returns a nonsensical answer. Under GCC 4.6, however, the compiler actually treats frexp as a built-in and bypasses InterX's broken math library. It was during this that I realized that Microsoft was essentially shipping a straight port of OpenBSD's C library and math library. I had seen that services for Unix had the strl copy function, which is a secure string copy function that had originated from OpenBSD. Cementing the relationship further, OpenBSD had actually had a similar bug with xrexp, which was fixed in OpenBSD 3.7, suggesting that the bug had originated there and had ended up in services for Unix through the shared heritage. Still, this was the first time I needed to tap out on this project, but we're not dead yet. We have no tests and no plan B, but I knew of the next session we were going to start building our cross compiler and then Linux from scratch on Windows XP. A day later and we were off to the cross-compiling races. However, it wasn't so simple as just building GCC with a few extra configure flags. Oh no, it's much more involved than that. Fortunately, I did have some help at this point. I suspect most of my viewers are familiar with Linux from Scratch, which is an online book that documents how to build Linux from scratch. What you might not know is there's a variant of that book known as Cross Linux from Scratch, or CLFS, which, well, do I really need to spell it out? The CLFS book basically lays out every component I need to build going forward, with patches, but with two major caveats. The first was that the CLFS book was last updated a decade ago. This wasn't really a big deal since I'm only using it as a reference. The second, slightly larger issue was that I was fairly certain that while this guide does accurately outline the steps to cross-compile a Linux system, it still kind of assumes that you're on a Linux system to begin with. It's more for dealing with cross-architecture builds than cross-operating system ones, and this would have implications later. I also didn't follow this guide to the letter, so if you're following along at home, do note that I diverge here. I had also installed Debian 9 in a fresh VM alongside things. While I basically wanted to keep this video on the idea of, if you only had Windows XP and a bunch of Linux source, could you build it? But I will make an exception to help test things. This VM was how I was going to know if my soon-to-build Linux kernel would work. I also used it to more easily download some of the source bundles I was going to need moving forward. But enough chit-chat, let's get to building. The first thing I ended up building was an updated version of File as a host utility. File is a system utility used to identify what a given file is. This, however, didn't build right out the gate. What a surprise. The first thing I discovered is that all the things I did to get std_int working didn't quite work. I ended up with the header on the installed GCC 4.6, but it didn't define all the types I needed. What I ended up doing is merging the generated header file with the copy of std_int mingw that I used back when building GCC, and this finally got a std_int header that actually seemed to work. The second build problem was a missing function, stir to ull. This function converts an unsigned long integer or a 64-bit number to a string. I had actually run into this problem when building Tickle, but the long and short of it is that Services for Unix lacks any sort of support functions for dealing with 64-bit numbers. The right way to fix this would be to provide an implementation of stir2ull. What I actually did was patch the code to use the 32-bit versions of these functions. It's not the correct way to fix this, but it would probably be good enough for what I needed it for. With that done, a file built, and we were on to binutils. Binutils, or binary utilities, is a GNU package that provides the assembler and linker. It essentially handles all the parts of manipulating binary executables and is used by GCC. This was also the first cross tool we needed to build. Let's take a brief moment and talk about the build, host, and target variables. Under the hood, packages using autotools, or in other words, a standard configure script, have 3 variables that can be set to define the build machine, host machine, and target machine. Build is obvious, it's the machine we're building on. Host, meanwhile, refers to the machine that we want to run the just compiled tool on. Target, meanwhile, is the oddball, and isn't something that most packages care about. What it does is say, we want to build output code for this platform, or in other words, it's the target machine architecture we want to build output code for. In the case of building a cross-compiler, our build and host flags will be set to i586 PC InterX 3.5, since that's our Windows XP system, and our target flag as x86-64 unknown Linux GNU, because I'm insane and decided that building a 64-bit system for Windows XP seems like a fun idea at the time. By saying the target flag here, we're telling binutilities that we want an assembler and linker that runs on Windows, but generates code for a Linux system. On paper, this is simple enough. After saying all the flags, binutilities started building and then fell over. The build failure this time was due to a missing multi-byte and wide character functions that didn't exist on InterX. There's a configure check that erroneously thought that these functions do exist, so a quick edit to config.h and we're rolling again. Sometime later, I had a built cross-linker and cross-assembler, our first steps towards actually building Linux software on Windows. I did spend a little time building 2 optional components, ILS and clog, which enable better code optimization in GCC. The downside here is I didn't check the version requirements of GCC 4.6 and ended up building 2 new versions of both, so I just continued without. That was a waste of 2 hours. Oh well, now we're at the point that we had everything needed to build a Linux cross-compiler, except not really, and this is where I need to talk about sysroots. Sysroots, short for system root, is the directory that holds all the libraries and header files for our cross-compiler to link against, such as our C library. If I was building a normal cross-compiler, I could just copy these from an existing Linux distribution and call it good, but that would violate the spirit of what I'm doing. As such, we're going to need to populate the sysroot from nothing, and this is where it gets tricky. To build a full cross-compiler, I need a C library built for Linux, which would require a cross-compiler to build. This is a circular dependency, but it's one we can break fairly easily. I just need a minimal cross-compiler, and fortunately, GCC supports this just fine. We can then use this minimal cross-compiler to cross-compile the GNU C library, known as glibc, and then build the full cross-compiler, giving us everything we need to build both the Linux kernel and what's known as userland. Of course, in the recurring theme for this project, it's not that simple. We need the Linux kernel headers first, as these define the kernel's programming interfaces. To get these, I grabbed a copy of Linux kernel 4.19. We can use the install headers target to simply install the development headers. Extracting the Linux kernel took a long time, like almost an hour. I actually did this in parallel with wrestling with binutilities, but while it doesn't come across while watching the video, this has been a slow and painful process right along. Now, at this point, I thought I was largely home free. Oh, how little I knew. While running headers install, I quickly hit a bunch of build errors. What I had failed to take into account are what are known as host tools, and this is a major problem. When building a piece of software, it's fairly common that build time utilities need to be created to process data files. These build time utilities aren't cross-compiled, they're built with the native compiler, and it's here where we hit a major snag. The Linux kernel has a utility known as relocs, which is used to list relocation segments in an ELF file. This utility is used to help link the kernel at the end of the build process and was apparently also built as part of the headers installation process. If you didn't understand any of that, don't worry. The short version is I need relocks to build, and that was a bit easier said than done. The relocks code depends on a lot of things that I just didn't have on InterX, such as a headers definitions file for the ELF file format, byte-swipe macros, and a lot of other little things. The key part here, though, is that these were definitions, not actual C library code, though, so I came up with an idea. I went to the Debian VM I had set up earlier and had started copying the header files from it to my InterX host system. Now, normally this isn't something you can do. Header files, especially those for system libraries, aren't something you can just copy and paste. However, because these files only contain definitions, there was a chance that I could just take these as is, edit them down to what I needed, and then with some luck, just have it all work. Now, I had wanted to do this project without using a Linux system at all, but this wasn't an easy stumbling block to get around, so I made an exception. After tracking down all the header files I needed, I went through and started making edits. This was actually a relatively straightforward process, aside from the fact that I also had to create a minimal int types.h file with some preprocessor macros to satisfy relocks into building. And get it building I did. I'm actually shocked that I got this to work, but after building relocks, the headers install process completed, and I had everything I needed to make a minimum build of GCC. After that, I needed to make a new build directory, enter an obnoxiously long configure command that basically disables everything but the absolute basics, and let it build. Aside from a single bit of minor tweaking in some Linux specific code so it could run on InterX, this basically worked exactly as planned. I now had a minimal, but hopefully functional, InterX to Linux cross-compiler. Here's the first time that we now have the host flag set to Linux, as we're building code that will run on Linux. Building glibc should be straightforward, aside from having to set a variable to disable stack smash protection, or SSP. SSP is a great security feature, which requires features in GCC that require a fully functional C library to build. Bootstrapping, gotta love it. Also, as an aside, I had to update Gawk to satisfy glibc's configure script. So, with configure complete, I ran gmake and waited. There was absolutely no way this would fail, right? No, of course not. The build failed. Due to stack smash protection still being enabled, I made a 1-character typo on the command line and didn't load config.cache. Now, I should note that up to this point, this footage has come from what had been ultimately a 10-hour livestream, and I was falling asleep in my chair. So I fixed the stack smash protection and let it run. It should be noted that while I've been dealing with performance issues with XP right along, so this build was particularly glacier, and as I quickly found out, there were still more issues to solve. But before we get into that, let's talk about those performance issues. I actually did run Crystal Mark Retro to get some idea of what was going on, as people were saying that this was Hyper-V or some other issue. My gut feeling was that the performance issues were due to SFU directly, but I wasn't sure. When running the test, Crystal Mark Retro said that the random disk read-write speed was 111 in the VM, which sounds about right for IDE drivers. On the host system, it was quite a bit faster, but I don't know. It doesn't seem like that even if I was bottled by IDE drivers, it shouldn't be this slow. I'm open to feedback below, but I wasn't going to go for the hassle of moving XP to another virtualization solution, which may or may not be faster, so I just lived with it. Also, since we're at the point that I'm asking for comments, considering hitting the buttons below, since it really does make a difference for the channel, and if you're already 30 minutes into this video, you probably want to see more content like this. Shameless plug aside, I had to get glibc building, and on top of that, a bunch of video editing left to go on this project, so I tackled the remaining glibc problems offline. The next issue was in SunRPC. It wanted to build a host tool to generate RPC definitions known as RPCgen, but it was failing due to missing internationalization features. Now, I had built glibc with internationalization disabled, that's the disable NLS flag on the configure line, but it apparently didn't matter here. A review of the code in question also confirmed that there wasn't an easy way to disable internationalization. Fortunately, there was an easy fix. I just needed getText, which has a full implementation of the internationalization API that RPCgen needed. Building this was fairly trivial, and I just needed to make a quick edit to modify the host compiler C flags to load getText. So, did that fix it? Well, it fixed the first failure. The next failure was due to variable typing issues. Interx's C library defines some of the same types that this code wants, but in a way that conflicts. Fortunately, Interx isn't the only platform that does this, so some tweaking to some pre-existing if-then statements got me rolling. And then it failed again. It was using 64-bit stat functions to examine files. I replaced them with 32-bit functions. Did it work then? Nope, this time due to missing C library functions, stp copy and stp ncopy. These functions are ones that exist in newer versions of the POSIX standard, but not in the version I had. The solution was to copy the implementation from GCC's Liberty library, throw them in an if-def, and then boom, RPCgen built properly. So was that it? Well, right now I don't know because it's still building. Hopefully by the time I'm done editing this section of video, it'll be done, or I will have more to say, so bear with me for a moment. So after letting it run overnight, glibc did actually build, although as I would find out, I didn't get it quite right. Still, at this point, I thought I was ready to start building the kernel, but there were some headaches there that I wouldn't find out until next stream. I kicked off the 7th stream in this series with the expectation that I was going to be able to build the Linux kernel this session. However, to do that, I still had to build the full GCC cross compiler. And this, of course, is where things went wrong. This stream was a little disjointed, so let me just present the problems I ran into and how I fixed or otherwise worked around them. Also, I probably made some bad choices in how I worked around or fixed various problems, but we'll get into that. First off, I discovered that my earlier C cross compiler couldn't quite build Linux binaries. It was complaining about a few missing files known as the C runtime, which handles initializing an application to run C code. In theory, the linker should automatically find these in the sysroot, but it wasn't working properly, nor could I figure out what I did wrong. I eventually determined it was looking in the cross-compiler libs folder, and I was able to copy the files to the right place to let things work. This let me build Hello World as a Linux binary from Interx, which was a good first step. Next, I had to deal with a slew of problems with rebuilding GCC. The rebuilt cross-compiler first encountered a bad configure issue where it defined uint pointer and int pointer types on its own, mostly because I had commented out lines in my edited stint int header file at some point and forgot to uncomment them. This led me down what can be best described as a rabbit hole of debugging, as GCC had given me a nonsensical build error due to this problem. It was only by looking at the preprocessor output that I could piece together what had gone wrong and fix it. Secondly, I needed to reinstall the kernel headers in my sysroot. I had put them originally in the cross-compilers include folder. So, who knows? I would have thought glibc would have failed to build if I did this wrong, but at this point I've given up trying to understand anything at this point and am kinda rolling with the punches. With the headers properly reinstalled in the sysroot, I got GCC building again. Until it died once again due to C runtime stuff. I clutched around this issue, but I had a bigger problem with glibc that I was going to need to fix. While not directly related to the C runtime issues I had misbuilt glibc due to setting glibc's configure prefix to /cls/user. This was wrong. Prefix on a configure line determines where something's installed to, but it also has an effect in how libraries encode paths internally. When cross-compiling, this caused the cross GCC to look for the library in the /clf folder of the sysroot, or in real file system terms, /clfs/clfs/user, which isn't right. You might have caught this mistake if you were looking closely when I showed the Hello World build failure earlier. The right way to fix this is to rebuild glibc with a prefix of /user, and then use make dist_dir equal /clfs install to make it install files in the proper place with the correct paths encoded. Or so I think. Part of my confusion here is that a normal Linux from scratch system builds its toolchain in a somewhat unusual way. Under LFS, the first stage system is built in a special tools directory, and then everything is rebuilt afterward once rebooted into the minimal system it generates. Cross Linux from scratch does the same thing, but I wanted to cross-compile everything instead of just making a minimal system and then rebuilding everything under Linux. I suspect as I write this, I'm just causing more pain for myself, but badly planned out hubris makes good video content. Honestly, I do think this video is becoming more of a guide of what not to do instead of rather an educational piece, but if nothing else, others can learn from my mistakes. We'll see how much pain these decisions make for me. For the time being, I made some links to make glibc's install path be valid within the sysroot and continued on. I will have to rebuild glibc later to correct this mistake, but the Linux kernel doesn't require glibc to build, so until I'm building the userland, I can put it off for now. I'm pretty sure I had to fix a few other things, but it literally took 6 hours just to get this far, and most of what I had fixed were due to mistakes I had made earlier. To make a long story short, this sucked, but in the end, I did end up with a fully featured cross-C and C++ compiler with all the major features enabled. Now I'm finally ready to build the kernel. I should note that between streams, it was pointed out to me that kernel 4.19.325 was the actual LTS release. Prior to this, I was using 4.16 for kernel headers and such. It's a small difference, but 4.19 was supported until the end of 2024, so it is, in effect, an almost modern kernel. I'll have to update the kernel headers in the sysroot, but since I also have to rebuild glibc as is, it wasn't a big deal to switch versions at this point. As for building the kernel itself, I thought I was ready. However, this is where the problems really started. Like before, the kernel needs certain utilities to be built for InterX, first of which is kconfig, which is the kernel configuration utility, also known as the thing that makes makeconfigure work. Kconfig had a few things I needed to work around, such as missing string handling functions that I had to provide alternate implementations, and weirdly, getopt. Getopt is a function called used to parse command line options, and the base function is provided by InterX. However, kconfig uses a GNU extension known as kopt-long to provide long command line options. Honestly, I could have probably just fixed the code to use InterX's getopt implementation, but I didn't immediately realize that the base getopt function was available, so I just took getopt and getopt-long's implementation from Android's Bionic C library, stuck it in kconfig, and called it good. At least Android's C library is BSD licensed, so when I make a full copy of my source folders for others to poke at, it's not going to be a big deal. If it seems like I'm kind of throwing shit at the wall and seeing what sticks, then yeah, kind of. Honestly, this entire project has proven far more difficult than I expected. If I was trying to make a reproducible or sane build, I'd be doing a lot more work for what was just a fun project for myself, although I'd probably be cobbling things together at first as I am now, just to see what does and doesn't break. Getopt wasn't the only problem I ran into. Several string handling functions were missing, such as stir and dupe, which I replaced with some hacked together code that mimicked the functions of the original and seemed to work, mostly. For instance, I replaced stir and dupe with stir dupe without properly handling the null character, which led sh spitting out a bunch of errors a bit later on. This led me to naively assume that the system sh was too old, so I just replaced it with bash. Okay, in my defense, InterX ships with a copy of Korn shell from 1988, so it stood to reason that the sh shell was of similar vintage. It was only after bash died the same way did I realize my mistake. As it would turn out though, I would have to upgrade sh later on, but we'll get to that. After getting kconfig sorted, I could actually attempt to kick off an actual kernel build, but nope. The problem now is I need to go through and build a few more missing dependencies. The kernel requires a few utilities such as Bison and Flex to build. These weren't terribly hard to install or update, but I also found that I had to update the system calculator, BC, to make everything happy. Also, Flex required me to update M4, a macro programming language which is also used by AutoTools. So after going down that rabbit hole, things died again. Now the kernel was complaining that I didn't have a ret pull line compiler. This is a compiler feature to help mitigate the effects of processor bugs like Spectre. That requires GCC 8, but I can disable ret pull line in the kernel config and carry on. Of course though, that wasn't enough to make it happy. This time the kernel wanted elf utils. Unfortunately, this wasn't something I could build. Elf utils depends on a GCC feature known as thread local storage, or TLS. TLS allows a variable to be local to a given thread, but it wasn't a standard C programming feature until C11. For the time period I was working in, well, GCC supports this feature on Linux and Visual C++ supports this feature on Windows. However, on Interx? Nope. TLS requires C library support, and I'm fairly sure there was no way I could enable or hack it in. So was that the end of this project? Well, it might have been if elf utilities was a mandatory dependency. As it turns out, if I disable certain flags in the kernel's config file, I can build a kernel that doesn't require elf utilities to be installed, bypassing the problem. I did find out after the stream that GCC does have some ability to emulate TLS on platforms without native support, but I had no idea if I could get that to work on Interx, and if I don't need it, I'm not going down that rabbit hole. My toolchain is held together with duct tape and spit as is. Okay, so are we now ready to build the Linux kernel? Nope, I needed OpenSSL. Oh boy, can you tell that I'm getting tired of reverse dependencies? This is needed by the kernel's cryptography subsystem, and unlike the elf utilities dependency, I wasn't getting out of this one. However, building OpenSSL immediately failed, complaining that my 2003 era of Perl was too old. I might have broken at this point. Are you kidding me? No, I gotta upgrade Karl. Help. If you can't tell, this project has proven to be a struggle all the way, but if I could get the Linux kernel built, it would be mostly downhill from there. Everything else was relatively simple cross-compiling, and I wouldn't have to deal with Interx's C library or missing functions. So, Perl. Despite my manic laughter, Perl is the superglue that has held Unix and Unix-like systems together for decades, and I didn't actually expect any major issues building it. Running its configure script, though, revealed a new problem. At some point, I lost dev null. As in, it was a text file complaining that package config was missing instead of the device node it should be. Now, I should note that dev null was present on my system earlier, so I have no idea how I lost it or how it became a text file. I assume a configure script at some point had clobbered it, but this is an entirely new failure mode for me. I'm starting to think that Interx hasn't been very happy with the amount of misery I'm putting it through. It's here where I decided to take a snapshot of my VM and then run Interx's repair utility from the install CD. This would hopefully make everything right. It was a good thing that chat urged me to make a snapshot as well, since I was going to need it shortly. After repair run, I was right, I did have dev null. However, Perl's configure script broke due to the system sh being too old again. I tried to replace it with bash again and I got access denied. No matter, I rebooted into safe mode, tried again, and also got access denied. In safe mode, where no Interx function was running. And I was able to remove the old sh, I just couldn't write a new one, at all, even as administrator. So yeah. I have no idea how I was able to do this before or why I couldn't now, but I'm learning to take Ooga Booga computing problems in stride now. It was at this point that chat pointed out to me that the manual page for the null device had the commands in it needed to recreate it. I was flabbergasted. Useful documentation, what a novelty. I have to assume that dev null disappearing was something that the Interx developers had run into before because it listed everything I needed. So I rolled the VM back to the snapshot I took, reloaded it, and recreated null with make node. This then let the Perl configure script run and it started building. Finally. It was at this point that I had been streaming for 11 and a half hours, and my brain was literally putty at this point, so I shut the stream down and called it. Perl did build successfully, but its test suit hung halfway through. Genius me forgot to record that clip, but I need Perl for just one thing, so I'm going to assume it's good enough and carry on with my life. Now I just had to get OpenSSL built, and with that I would know if my quest to build the Linux kernel was in vain or not. If I actually got a working Linux system out of this, it would be an actual miracle. Diving back in, I had one goal for what would be an 11-hour stream: get the Linux kernel built. I decided at this point that if I either couldn't get the kernel built soon, or if I built the kernel and it failed to boot, I would call this project done. I was now 3 weeks into this project, and well, it was starting to get to me. What stood in my way was OpenSSL. My first attempt at building OpenSSL went well, and by that I mean it broke entirely. It identified the build platform as UNIX 7, and predictably, the build fell over shortly thereafter. No matter. OpenSSL uses a bespoke configuration system written in Perl, which had no concept of InterX. That hadn't stopped me before, so after getting my bearings, I set to work. I started by trying to use the BSD generic 32 target as a basis to build on InterX. That's because InterX itself mostly resembles a BSD Unix. This worked better, but I still had to do a fair bit of tweaking to get things building. Along the way, I learned quite a bit about InterX's network stack. For one, it doesn't define the socklen-t type, which is easy enough to work around, but I realized in the process that InterX's networking layer appeared to be directly built on top of WinSock. This probably isn't an earth-shattering revelation, but it does appear to be the one area that is largely custom code in InterX instead of being based on ancient versions of OpenBSD. If the headers are to be believed, InterX's network stack is capable of generating not only standard IP packets, but also IPX, NetBIOS, and AppleTalk. These are all protocols supported by Microsoft's networking library, although there's a rather notable absence of IPv6 here. Now, a lot of people might tell me that XP didn't support IPv6, but that's actually not true. It just wasn't enabled by default. You can add IPv6 support to an interface and network connections, but that's neither here nor there. Honestly, it might be interesting to come back to this and try and get this functionality to work, although I'm not sure what AppleTalk software I could build besides maybe NetAtalk. Getting back to OpenSSL, after a lot of pain, I did get it to compile. Linking though, well, the Microsoft supplied LD was, shall we say, less than happy. It kept dumping BFD assertions, although I did end up with a built libcrypto, libSSL, and OpenSSL command. A working SSL? Not so much. Trying to run any of the test code or the OpenSSL binary immediately crashed. GDB said that we were dying in memory allocation functions, although given every GDB experience up until this point, I didn't trust it to say the least. Part of this may be the flags used to build a shared library. When building a shared library under InterX, you need to give the -shared option as well as provide a randomized based address for the library to load to. Due to the way the OpenSSL build system works, this isn't super trivial to do right, nor did I immediately figure this out at the time. Furthermore, OpenSSL's code is, how to put this nicely, a nightmare to debug. It uses custom implementations of malloc, and a lot of the code is extreme spaghetti. It's actually the main reason why LibreSSL, a fork of OpenSSL, came into existence after the Heartbleed bug came to light in 2014. So I put OpenSSL aside because at this point, I really didn't think I was going to get it working and tried to build LibreSSL. LibreSSL replaced OpenSSL's bespoke configure system with AutoTools, which does know how to work with InterX. The biggest problem is it wanted things like IPv6 support. So I just started commenting out code. I didn't need much of LibreSSL to build, but let's be clear, this isn't a way to fix things, and well, a rather infamous security vulnerability was once introduced into Debian by coming out and refactoring code in cryptography libraries many years ago. As a former Debian developer, I was no doubt invoking bad juju by doing this, but as I kept working on it, I kept feeling like this wasn't going to work. Thus, after about 45 minutes, and encouraged by chat, I took a second look at the OpenSSL dependency in the kernel to see if I could somehow get around it instead of descending deeper into this madness. And, spoiler alert, I could! Turns out my little expedition into the security libraries in Perl was entirely unnecessary. Although without Perl, I wouldn't have known about my dev null problem, so I guess this works out in the end. Despite the kernel documentation saying that OpenSSL is required to build, it is actually possible to disable enough feature flags to allow the kernel to build without it. To do this, I was going to need an actual way to look at the kernel's config and modify it, which meant getting menu config to work. This required building end curses, which went mostly smoothly. I did have to set f permissive for it to build since the combination of C++ code, my hacked up stdint header, and probably the phase of the moon made GCC fairly unhappy, but build it did. After that, I could run menu config, and man, it was surreal seeing this running in a Windows console. I'm actually surprised it worked. I was expecting an end curses application to break and having to telnet into InterX to give it a kosher enough console to render. It wasn't 100% perfect, and like the arrow keys didn't work, and the redraw rate was very low, but I could navigate the menus and start making modifications. What I needed to disable was config keys, and to do that I had to go through and find every option that was forcing it to be enabled and disable them. This included system integrity options, Wi-Fi support, NFS-v4, and probably a few other things, but I eventually got to the point that I could mark config keys as unneeded, and thus OpenSSL was no longer needed to get a kernel build going. Hurrah! I could now attempt to build the kernel, but if you thought I was out of the woods here, you'd be wrong. Shortly after starting the build process, the compiler hung trying to generate the kernel's time constant functions. Time constant, or time const, handles a bunch of internal definitions within Linux for measuring hertz and everything related to time, so yeah, it's kind of an important component. This file is dynamically generated by, get this, a script for the system calculator, BC. Now, if you've been paying attention, you'll remember that I actually already upgraded BC earlier in this epic project, but it was hanging now. There was no test suite in BC to give me hints as to what might be wrong, so I got stuck here for a while. By running the build in verbose mode, I could see that it was trying to generate timeconst.h by giving BC a time value of 1000, and some testing showed that BC was hanging trying to read the value in from stdin. So instead of fixing this properly, I just modified the kernel's calculator script to hardcode in the 1000 value, and sure enough, that allowed timeconst.h to generate and the build got going again. This was definitely a first. I never had to debug a BC script before, and I honestly don't know what caused it to hang here, but whatever, we're rolling again. Not long after though, I reached a much harder to resolve build failure, VDSO2C. A little technical background is needed here. VDSOs are virtual dynamic shared library objects, and they're small parts of kernel code that are exposed to running programs to let them access parts of the Linux kernel. VDSO code isn't actually run in the kernel directly, it runs in user space, but the VDSO objects themselves are built into the kernel image. The problem here is how the VDSO code is built. The VDSO code is first built into an object file by our Linux cross-compiler, then a host utility, VDSO2C, is built for the build platform and used to convert the just built VDSO objects into a C file with additional metadata, and then the final result is built into the final kernel. The problem here is that VDSO2C generates a bunch of C code dynamically, and that involves 64-bit values that have to be converted to strings that are printed into the generated C file. You know what I don't have? 64-bit integer support in my C library. This was actually a really big problem because if I got the VDSO code wrong here, I would end up with a broken kernel. Furthermore, while I'm building a 64-bit kernel, a 32-bit one wouldn't have saved me since this code always uses 64-bit values. Right. So my choices here were to either implement a function that could take a 64-bit value and turn it into an ASCII decimal number, or somehow generate the right value another way. Maybe it would have been easier to do the former, but I decided to do this in hex. As far as generated C code goes, it doesn't make a difference if I outputted the 64-bit offset it needed in decimal or hex. I just need the number to be correct in the generated code. By doing it in hex, I could simply print out the lower 32 bits of my 64-bit value as is, then take the top bits, barrel shift them down 32 bits, and then print them in order. I spent a fair bit of time testing that this would actually work properly and wrote a patch that did just what I described. I wouldn't know if it would actually work until I tried to run my resulting kernel, but it was enough to get the kernel building again. That is, until it fell over again. The next two hiccups, though, were fairly simple. The first was that the whoami command on interx had stopped working. It turns out that whoami on services for Unix actually is a shell script that determines the current logged in user, and it was unhappy that I replaced sh with bash. Fortunately, I had saved the old shell, so a one-line change got it running again. The second one was a missing make temp command, which creates a temporary file or directory. I'm actually surprised I hadn't run into this problem previously, but make temp was being used to stage some files for building intramfs support in the kernel. I did kinda want intramfs support, so I went to build core utilities which had make temp and a bunch of other programs. The logic here was that interx's dated userland was already causing me pain, so I might as well upgrade it. Unfortunately, core utilities configure script fell over after about 15 minutes due to the fact that it couldn't figure out interx's mounting system, which is to be expected since interx doesn't have a mount command or mount points at all. But that left me in a creek without a temporary folder. I could probably get the rest of core utilities to build, but I decided to shelf it for now. Disabling intramfs with menu config was enough to get the build going again. Surprisingly, at this point, things just started working, at least for a while. It took quite a while to reach the next hiccup, which was relocks. I talked about relocks before, but as a reminder, it's a utility that prints relocations in an ELF file and is used during the build process to help let the kernel locate its own components when both building and booting up. The problem here is that relocks kept complaining that the file it was reading was an unsupported type, which very much is a problem. I had built relocks out of hacked together ELF header files, and it was being held together with magic pixie dust, which is never a good thing while debugging. So before getting anywhere, I needed a known good relocks to compare it to. What this boiled down to was quickly compiling kernel 4.19.325 on my Linux VM so I can compare the results side by side. I should note that the full kernel build running on W9 completed in about 6 minutes. Meanwhile, it had taken about 45 minutes for my build under Windows XP to explode, just to give you an idea of what the general performance was like when doing this. It should also be noted that when building under XP, my processor cores were running flat out. I wasn't I/O bound at all, it was just that slow and likely unoptimized. Anyway, getting back to relocks, by comparing the working relocks command on Linux to the broken one I had on interx, I quickly determined that it looked like I had a byte ordering problem, and here is where I need to talk about endianness. Different processors handled numbers differently. Some place the most significant bit in memory first, which is known as big endian, while other processors place the least significant bit first, which is little endian. If this sounds like an entirely arbitrary difference, well, it is, and the term endianness actually comes from the book Gulliver's Travels by Jonathan Swift. In the book, endianness refers to the proper way to crack open a hard-boiled egg, and disagreements on such trivial matters are a major source of strife and political divide. However, despite being a trivial difference, endianness is something that I and the Linux developers need to care about when reading data values. The data values were being read were in little endian format, and Intel processors are little endian by design. So at some point, the values I were reading were getting byte swapped. Why this was happening was due to one of the most absurd behaviors I've seen out of the C preprocessor. In relocks, this block of code is used to determine if the values read from an ELF file need to be byte swapped. If we're on a little endian platform, they're passed through as is. If we're on a big endian platform, they're byte swapped and then returned. The code in question depends on the preprocessor macros, byte order, little endian, and big endian. These on Linux are defined in endian.h and ultimately should have come from the predefined macros set by the C compiler. I had copied the endian headers from my Debian system as interx doesn't include them. Apparently, I was missing a bit of magic because, as it turns out, none of these endian macros were set, which you'd assume would call all these if preprocessor macros to evaluate to 0 and thus get excluded, but no, that isn't what happens. What actually happens is that if you compare an undefined value to an undefined value, they equal each other and thus evaluate to 1, and thus the big endian code and the little endian code were getting enabled. As the big endian code is after the little endian code, it replaces the earlier definition and causes all my values to be bit swapped. This actually did cause a warning while compiling relocks, which was ultimately my tip off that this was happening. But yeah, I actually went into my endian.h header, properly defined little endian and byte order manually, and then rebuilt relocks, which started returning reasonable looking data. Ugh. That was really annoying to figure out and solve. I decided to make clean here because if my byte ordering macros were broken before, it was likely other bits of code were miscompiled. After clean finished running, I kicked off the build and waited some more. Surprisingly, it seemed like everything more or less was working at this point. The build slowly grinded through the drivers, and it got to the point it actually linked VM Linux, which is the penultimate step to creating a bootable kernel image. It was right here at the finish line, my crappy Interix userland decided one last FU and kicked out an xargs error. I'm pretty sure this is due to xargs not supporting the recursive argument, but surprisingly, the build didn't stop. It instead decided there were no modules to build and went right on to building a BZ image file. It then spit out an error disliking my ln command and then finished. A quick examination seemed to show that I had a valid BZ image file ready to go. I didn't have the modules built, but I wouldn't need them just to test if I had a working kernel image. I quickly FTP'd over the just built BZ image file to the Debian VM and modified grub to load it. Now it was time to reboot the VM. Would you look at that, a Linux kernel built on Windows XP booting up. It fell over a few seconds later with a kernel panic, but those were boot messages. I couldn't see the actual cause of the panic though. Normally you can use Shift Page Up to scroll up on the console and see previous output, but either that option was disabled or Hyper-V's console wasn't translating the key presses. I quickly set up a virtual serial console and set up PuTTY to capture the full boot log, which revealed, as I expected, it didn't like the root dev option I set. Turns out the root file system was on SDA1 and not 2. Oops. Fixing that, I was in fact able to boot into a fully usable system. X even worked, although neither the mouse nor networking did. Still, that means I did it. A Linux kernel from scratch built on Windows XP with services for UNIX. What an odyssey. I wasn't done yet though. I still had to build the rest of the system, but this was the 90% mark for this project, which meant that the most soul-crushing but straightforward 10% remained. I had to fix the issues with Interix's userland to make the kernel build system fully happy, as I did need the modules. I also still had to deal with building the userland and how I was going to boot this thing, which was mostly a lot of compiling, but at this point I had reached the top of the cliff. Now I just had to push to the summit ahead. It was almost a week later before I picked up this project again. Between streams, I did rebuild glibc to fix the configuration issues I talked about earlier, and also reinstalled the kernel headers. This wasn't strictly speaking necessary, but I figured while I was here, I might as well. What was next was going to be easily the most time-consuming part of this project. I needed to build the userland, which is the collection of tools and utilities which surround the Linux kernel. My initial plan for my first stream back was to tackle this, but I realized shortly after starting I had made a mistake. I hadn't moved the old sys root out of the way, so the links I made as a kludge caused make install to put things where I didn't want them. Great. So I kicked off make install again after clearing the root and got to work. I knew that was going to take a few hours since, unfortunately, glibc's makefile is massive and make runs very slowly on services for Unix. That also put my plan of building the userland essentially on ice, since I can't really build anything without the C library sorted. However, there were still a few things I could work on, namely, how was I going to boot this thing? In keeping the theme of building everything from Windows, I now had to figure out how I was going to make bootable media of sorts. Ultimately, to make a usable Linux, I was going to need to partition a hard drive and install a bootloader. That meant that I needed parted, E2FS progs, and grub at a minimum. However, even if I could build those, I still needed a way to run them under my just built Linux kernel. While it might be possible to use a file system add-on to add ext2 support for Windows XP, ideally I would prefer to partition and install under Linux with my just built kernel and cross-compiled userland. There were a few ways to tackle this, but in my mind the easiest and most efficient way would be to netboot the system. Services for Unix does include an NFS server that would let me theoretically do this, although even at this point I had some reservations on if this would actually work. The main problem here is permissions. The NFS server shipped with Services for Unix maps Windows-style permissions and then remaps them to POSIX ones. This has some interesting implications for booting a Linux system, as certain files must be owned by root or other users to have a fully functional system. That said, I didn't exactly need much to work. Even if I could only boot into bash, as long as I could run parted, tar, and a few other commands, I was in business. However, this would be a little easier said than done. For Intel-compatible systems, diskless booting is accomplished by something known as PXE, or pre-boot execution environment. PXE uses DHCP to configure the network, download a first-stage bootloader via TFTP, and then downloads the kernel, which handles the process of loading the NFS root. On traditional Linux systems, this normally requires setting up a DHCP server such as ISC DHCPD, key, or DNS mask. However, this is a Windows system, and there's an easy solution in the form of TFTP64, which basically handles everything I need in one easy package. Despite the name, it is available for 32-bit Windows, and it does work on Windows XP. The problem was finding a copy, and then Windows Defender. And when I say Defender, I mean the copy on my host Windows 11 system, but we'll get to that. TFTPD64 was hosted on Bitbucket, which unfortunately had its archives purged about 2 years ago. Mirrors of TFTPD64 do exist, and with help from chat, I did find one. The problem here is that the download suddenly got flagged as malware by Windows' anti-malware protection. I'll be blunt, overriding these warnings isn't something most users should do, and I was wary that perhaps there was actual malware here at play. That said, this is almost certainly a false positive, and I'd seen reports about this online. The project was open source, and while I could conceivably build it, I didn't have the right version of Visual C++ for XP on my NAS. Also, I really didn't want to go down that rabbit hole if I could avoid it. However, this left me with actually getting the files downloaded. Chrome flat out refused to let me download the file, and there was no way to override it. I was able to download it from the command line in the subsystem for Linux shell, but the moment I tried to copy it over to the XP VM via my web server, Windows Defender jumped in and quarantined the file. As far as I could find, even with help from chat, there was no way to easily get Defender to restore the file or flag it as a false positive. So yeah, my efforts at making a netboot system were foiled by overzealous anti-malware protection. What I ended up having to do was download the file in my Debian VM, and then I was able to FTP it over to the Windows XP machine, where it loaded just fine. I did make a snapshot of the VM just in case it was actual malware, but at least so far, I haven't had my XP system pwned as far as I can tell. It was also unnecessary because it was at this very moment, as I wrote this script, I remember that it is possible to actually boot the kernel directly from UEFI via a kernel feature known as the EFI stub. This puts a header on the kernel binary and means that I could just put the BZ image file on a CD image or USB stick and boot it that way. That was probably going to be handy, but past me hadn't realized that yet. Getting back to past me, they were figuring out how to get PXE Linux built, or not built as the case may be. PXE Linux is the first stage netboot loader, which is loaded by a netbooting system during PXE and then is used to start the Linux kernel. Bootloaders are kinda a special case when cross-compiling, but to make a long story short, I wasn't able to get it to build. From what I can tell, PXE Linux, which itself is part of the syslinux package, can be built on Windows with MingW or under a Linux system, but it doesn't otherwise support cross-compiling natively, nor did it support being built under Services for Unix. It did partially build, but it didn't like the linker I had, nor could I build it with a 64-bit toolchain. This was something though that I could come back to later, since I was fairly sure this was a solvable problem. Also, as an aside, the make clean step of syslinux failed due to xargs, which was similar to the error I got when building the Linux kernel, which was my cue to build find utilities and get a new xargs command that was a little less of a dinosaur. But back to PixieLinux. I suspect I could get this working, but for the moment I just wanted to test if my approach to netbooting was viable. So I took a shortcut and found a precompiled copy of PixieLinux on GitHub, punted it into my VM, and called it good. If I do end up doing netbooting as my actual install method, I'll figure out how to build it from source, but right now I was testing to see if this was even viable. The next step was setting up TFTP-D64 with all the proper options, and then creating a new VM hooked up to my virtual network to netboot. After some fiddling, I got PixieLinux to load and got my XP-built kernel to start. That's progress, but it wasn't actually enough to boot up the system. First, I didn't have an NFS share set up with a viable root file system, and then it suddenly occurred to me that I had forgotten something critical. My Linux kernel lacked network drivers for Hyper-V, so going any further wasn't going to get me much, since while I could boot the kernel, I couldn't do NFS root without a network device. Adding those drivers wasn't terribly difficult. I just needed to go back into menu config, turn them on, and then rebuild the kernel. So I did just that. While usually rebuilding the Linux kernel is a quick operation, I had to turn on quite a few flags to get Hyper-V's guest support enabled, so instead of a quick kernel build, we were stuck watching make slowly grind through the kernel's source files. Not a big deal, since at this point I still had to take a closer look at how Interx's NFS server works. To make a long story short, Interx is a method of mapping Windows users to Unix users. How this works is a little unclear to me, but by bumbling through the documentation, I was able to set up a mapping of administrator to root. I did have to make a local password and group file to make this work, and then tell Interx to use them, but it was relatively straightforward. In corporate networks, it is possible to tell Interx to load a Unix user map from Active Directory, presumably using Microsoft's NIS server emulator. I admittedly kinda did want to play with this feature at some point, but at least for the time being, I really didn't feel like setting up Windows Server 2003 or Active Directory. Furthermore, this project was already proving to be a beast, and making it more complicated wasn't going to help anyone. After doing that, and some fiddling with the NFS admin command, I was able to make an NFS export, and then mount it in my Debian VM. It's kinda wild seeing NFS working from a Windows XP host. What came next was finding something to boot. At this point in the stream, glibc was still cooking in the background, as was my Linux kernel. So I decided that just for a test run, I'd put a minimal copy of Debian on my NFS share and boot into that. That would let me test my kernel working against a Windows XP NFS root and tell me what else I needed to do. Building a minimal Debian system is easy. You just need to use the bootstrap command, but when I tried pointing it at the XP NFS share, it errored out saying it couldn't make device nodes. That was a problem. Unix and Unix-like systems like Linux have special files that represent accessing hardware or other specialized functions. We saw part of this earlier since dev null is a device node representing a write sync, but device nodes represent all sorts of raw hardware access and are used for things like installing a boot sector or partitioning a hard drive. I could work around this with a temporary file system once I get booted into Linux, but debootstrap wouldn't let me continue as is. So I just told debootstrap to make a minimal Debian system somewhere else and then copied it via NFS over to the Windows XP VM. This would be my testbed to see if I could actually boot my kernel with a file system loaded off NFS from XP. But then something happened. Shortly after copying the Debian minimal root over, XP crashed and took the glibc make install process with it, which had been running for 3.5 hours up to this point. I loaded back in, started it and the kernel build again, and it crashed again. I get the feeling I was pushing the limit with Interx right about now. I loaded in a third time, restarted the build process, and this time the VM stayed up. but now I was curious as to why the system had tapped out. Plus, I wasn't going to get anything done until either the kernel build or the glibc build had finished, and I had just lost almost 4 hours of progress, so I need something to get my mind off that. When Windows crashes with a blue screen, it writes down what is known as a dump file on its way out. By default, this is a mini dump of the kernel's crash log, and is also what's sent to Microsoft if you send them a crash report. By using WinDebug, it is possible to read in the crash file and see what exactly went wrong. While I didn't have a copy of Visual C++ on hand, what I did have was a copy of the Platform SDK for Windows Server 2003, which also helpfully includes debugging tools for Windows. This was a holdover from all that work I did on Space Cadet Pinball a few years ago, and the files had just been chilling on my NAS up until this point. So I copied over the Platform SDK CD, loaded it up, and installed the debugging tools. I then attached a WinDebug to the crash dump and tried to read it out. This of course ran into the entirely predictable problem of symbols. Symbols are debugging aids that convert binary addresses into human-readable names. WinDebug is capable of downloading symbols from Microsoft Symbol Server automatically. However, WinDebug on Windows XP does not support the modern encryption protocols that Microsoft's Symbol Server requires, so it failed to download. I had actually thought that said symbols were purged, like so much of Microsoft's older knowledge base and tools, but nope, it turns out the XP symbols are still available. I just need to download them by hand in a modern web browser and copy them across. Thank you to this random Stack Overflow user who pointed this out. I could probably use Nginx to do SSL termination as an intermediary to allow WinDebug to just work, but I only need to download free files by hand. After which I was able to run Analyze, which told me that the NT kernel had bug checked in, drumroll please, ntfs.sys. Yeah, it died in the file system code. This actually isn't that surprising in hindsight, since Interix uses functions of the NTFS file system that aren't regularly used on most Windows systems, like links and case sensitivity. Furthermore, I'm running on a 6-core setup in the VM, which was rare in XP's lifespan, then thus it's not exactly surprising that I'm causing things to break. There's not a lot I can do about it, but just try not to stress out the system as much and hope it doesn't crash again. I stayed on air a bit longer past this point, but with both the kernel build running and glibc build running, there wasn't a lot I could do, so I eventually closed it out. This stream wasn't exactly productive, but I did learn a lot, and I had a fun detour into debugging Windows land. So there's that. As compared to the last stream, the next two were the opposite. I got a lot done. While the topic of booting was still on my mind, I just decided to work on building the userland first. glibc and the Linux kernel had built overnight, so I was ready to get cracking. Now, I apologize if I speedrun through this because this is both very samey and is essentially the same stuff we've seen before. A lot of the process going forward is run a configure script with the host and build options set, run make, and then install it with dest-dir. A few people may be confused as to why I'm doing that last bit with dest-dir, but we'll get to that in a moment. As I've said before, on paper, cross-compiling is easy. The first package I built this session, readline, built without issue. However, we were in familiar territory again when the second package I built, bash configured just fine, but fell over because it was using a linker flag called rdynamic. This was used in building a host utility and is one of those examples where cross-compiling just doesn't work right. rdynamic is used when building shared libraries on Linux, but isn't used on Interix. Some tweaks to the makefile, and I was rolling again. Bash built, but this is where we start seeing the main issue with cross-compiling. Up until this point, I've largely fast-forwarded through the configure script output, but it's here that there are a few things to point out. When cross-compiling, certain tests can't be run, so either configure has to make a guess, disable an optional feature, or error out. We can see this here where configure disabled certain features. In this case, the end result is a bash that has had its process substitution features disabled, which, at least according to the CLFS documentation, can cause glibc's test suite to error out. While there are ways to tell configure that everything is fine, I just decided to rebuild it under Linux later. From Bash we move on to core utilities, which, as the name implies, provides, well, core utilities like ls and more. This one basically built without issue, but due to configure checks being unable to run, the df utility was disabled. That's another one for the rebuild it again later pile. At this point, I decided to tackle something a bit harder, and that was the native Linux compiler. In effect, I had to now cross-compile GCC itself to make a native Linux compiler that would run on Linux. Like when I built the compiler before, I would also need GMP, MPFR, and MPC. As far as cross-compiling goes, this went mostly smoothly. GMP built successfully but got unhappy during the install step. As far as I could tell, the problem was somewhere in libtool, and it looked like it wanted to do something with rpaths and such. Rpaths are a feature in ELF binaries that essentially help programs find libraries without the need for LD library path. I wasn't sure what it was trying to do, and honestly, looking at my footage a few days after the fact, I can't quite tell you what I did to fix it besides removing the rpath argument. It also had problems with library versioning, which I got around by moving a few files by hand to where they needed to be. MPFR built without issue, but MPC ran into our first file path issue. When I've been building software, you might notice that there's a specific configured flag called prefix, which denotes where a given piece of software is going to be installed to. On native systems, prefix does exactly as told, but when cross-compiling a running system, it's a bit more complicated. Right now, our set of cross-compiled system files are in /clfs, but on a running Linux system, they'll be in the root directory. That means our prefix won't match a running system, and that's what bit me earlier with glibc. To get around this, I configure with a prefix of /user, and then use the -dir option when I run make install, which in most packages tells make to place the files in a given directory, and then apply the prefix directory to that. So if I configure with a prefix of /user, and then set -dir to /clfs, it gets everything installed in a way that works for cross-compiling and running said cross-compiled binaries. The only catch here is that sometimes this process doesn't work as you'd expect or can have some weird quirks. Case in point, MPC. What happened here is that MPC uses something called a libtool script to help the compiler or cross-compiler link with it. In this case, the script got generated with a path that's suitable for the native compiler, but our cross-compiler got confused by it. In theory, these sorts of issues should automatically be resolved by the sysroot mechanism, but as we can see here, it's not foolproof. The fix was a quick edit to change the path so our cross-compiler would be happy, and then afterwards, edit them back so we'll be able to native compile later. Next up, I tackled zlib. Zlib is a compression library that implements the deflate algorithm used by gzip. I didn't need to build it prior because both bin utilities and GCC have built-in copies that are used by default, but since I was building the system for real now, I decided to do it. Zlib is a bit unique in that it uses a homebrewed configure script instead of the auto tools based ones that we've seen up until this point. What this boiled down to is that in practice, I simply needed to specify all the cross tools by hand to cross-compile it and then install it as normal. That handled all the pre-dependencies, so it was on to the main event. First up is bin utilities. Bin utilities handles everything to do with binary files and has both the assembler and linker we'll need for Linux. Fortunately, bin utilities was pretty trivial to cross-compile, and thus our Linux system now had a linker and an assembler. This brought us to the big fish, GCC. I've already talked about this to death, but to sum up, I'm still using the same GCC 4.6.3 source tree that I've been using right along, with just the host flag set for 64-bit Linux. I kicked off the build and then looked for something to do since it would take a number of hours for that to finish. What that something ended up being was tackling the netboot issue from the last stream. As I stated earlier, the rebuilt Linux kernel with Hyper-V networking support was done, so now it was time to test it. I first tried to boot into the Debian root file system I had made previously, and much to my surprise, it basically worked first try and came up multi-user and dropped me to a login prompt. Honestly, I wasn't expecting that, but I will take the win. So now knowing that I had a viable kernel, the question became, would it boot at all with my cross-built environment? I couldn't start multi-user since at this point I didn't have an int binary, but I could just launch bin bash by setting the int parameter. After setting up the CLFS folder as an NFS export, I rebooted my test VM and would you look at that, Linux booted up into an environment built from scratch from Windows XP. Well, aside from Pixie Linux, but we'll get to that. With GCC building and a few hours before it finished, I called the stream there. However, at this point, I very much started feeling myself burning out on this project. The finish line was in sight, but I still felt like I had a lot left to do. As such, I'm going to abbreviate the next stream here in an effort to make everything go smoother and prevent the video editing from bogging down. I decided to mark the endpoint of this project for when I could successfully boot the system multi-user, partition and install the file system, and then successfully rebuild the Linux kernel and GCC on the just built host system to prove that it was in fact fully functional and capable of self-hosting. I had intended to do a full LFS system from that point forward, but that would easily be another 20 to 30 hours of work on a project that I had already probably spent close to 100 hours on already. The next stream was essentially more of the same that we've seen. GCC had finished building overnight, and while it was a bit temperamental, it was able to build binaries after manually setting the LD library path and cleaning out the fix includes folder, which shouldn't have run at all. My need to set LD library path at all was no doubt because LD config hadn't been built, but that was on my list of things to build going forward. Ncurses required some fiddling, but was otherwise straightforward, and I also got check, a testing utility, built just fine. I tried to build diff utils, but this errored out due to InterX sort utility having limitations on size. I don't really need this one immediately, so I kicked this down to the list of things to be built on the native Linux system. Unfortunately, to build natively, I have to solve a few hurdles. Specifically, I need dev null, and as I stated before, I can't make device nodes on InterX's NFS server. I could do it if I had a temp file system, or just use Linux's dev tempfs feature to create a fully populated dev file system. The mount command would require getting util Linux to build. I did try to build the most recent version of util Linux, but it didn't like the old glibc. Conversely, an old util Linux died with a multilib problem. Solving this though, however, would be a problem for another day. It was quickly approaching a month since I started this project, and I was getting to the do or die point. I was fairly close to getting my cross-built Linux from scratch system being capable of building native software, but I just needed to get over that hurdle. After a good night of rest, I did get util Linux building by simply moving the libraries to where it expected to be. It wasn't an elegant solution, but it did give me a mount command. Finally, I thought I could native build and get things done. Oh, how little did I know. While the mount command did let me mount the dev file system, configure still had issues. However, I had bigger fish to fry, but for once, the fish got me. Earlier in the video, I was fairly confident that I could get Pixie Linux to build on XP. As it turns out, this confidence was kinda misplaced. I kid you not, I spent about 5 hours on stream trying to figure out a solution to this problem. The fundamental issue is that Pixie Linux needs to be built on a 32-bit Linux system. I also couldn't get it or its dependency, the Netwide Assembler or NASM, to build on services for Unix. I probably could have solved these issues with enough time, but at minimum, I'd probably have to build a full 32-bit cross-compiler, glibc, and more before I would have a chance to get it working, and that's assuming I could get NASM to build. Was it possible? Sure, if I put enough time into it, but I was already hitting my limit with this project, and let's be clear, I did try other things. I also stated that SysLinux, the larger super package that Pixie Linux is a part of, could be built under MingW under Windows. What I found out is that while there is support for doing this, it doesn't build Pixie Linux but the actual SysLinux binary itself. This would still work, albeit with some more hoop jumping required, but nope, I couldn't get it to build, even after tracking down a copy of both MingW for the compiler and msys for a shell for Windows. What I found out is that while there is support for doing this, it doesn't build PixieLinux or the actual syslinux binary itself. This would still work, albeit with some more hoop jumping required, but nope, I couldn't get to build even after tracking down a copy of both MingW for the compiler and msys for a shell for Windows. There was a way I could theoretically do it, but it would involve building Cume, then using that to boot the kernel directly via its kernel bootloader, and then building PixieLinux under that. But I'll be honest, it was just too much effort for a YouTube video, and I wasn't even done with this project as is. And before you ask, I did look at other boot options. First, let's talk about the UEFI stub, something I brought up earlier. This allows a kernel to boot directly from UEFI, and I thought I would be able to just use it to load the kernel directly. Just one catch. As it turns out, for that to work on a CD, you need to build an El Torito bootable CD image. This isn't hard if you're on Linux. On Windows, well, it was probably doable at one point, but I looked at multiple CD image creation tools and they either didn't work or XP compatible versions have long since fallen off the internet. Chad also made an extremely good point to me. If I was doing this in the early 2000s, UEFI would have been extremely uncommon. While 64-bit systems did exist that could use it, it was rare in practice. This was also assuming I could even build an El Torito image under XP in some form, and that was something that was far from certain. It just didn't feel right. But ultimately, at the end of the day, while there were other ways to solve the booting issue that didn't involve PixieLinux, they all required downloading a pre-built bootloader or additional third-party tools that were larger than PixieLinux itself. Effectively, it would be variations on the same theme. I couldn't find a way to build the bootloader from source on XP without having to double the length of this project. So in the interest of saving my ever-decreasing sanity and getting this video out in a somewhat timely manner, I took the L and decided to make an exception for PixieLinux as a bootloader. I had spent 5 hours in a single stream working on this, and I had poked it in several others, so I can at least say I made an attempt. I'm not happy about it, but I'd be less happy if I spent days, got nowhere, and found myself in the same boat. Maybe I'll revisit this at some point, but for now, we're rolling with it. Moving on from PixieLinux as our bootstrap method, I went on cross-compiling a bunch of other utilities I was going to need. These were file, find utilities, gawk, getText, grep, make, tar, patch, and gzip. I had to do some babysitting when a script or two would break or otherwise get confused, but there really wasn't that much to talk about through this process. Slowly but surely, I was filling out the base system utilities I needed to be able to native compile. This was time consuming, and frankly, I had been so frustrated after the PixieLinux thing, I ended up loading FT8, an amateur radio tool, on my side monitor, and took advantage of an opening on the 20-meter band to work a transatlantic QSO from Greece to Canada, which improved my spirits somewhat. A large part of these projects is knowing when to take breaks, if for no other reason to keep one's sanity in check. Eventually, I did get everything built and took a stab at building diff utilities on the Linux system directly, which would be the first bit of kit that would be built for Linux on Linux. Unfortunately, this didn't go quite as planned. Configure kept dying in strange and unusual ways, and Make didn't want to play ball at all. It was right at the end of the stream that I made a worrying discovery. As part of the build process, GCC parses various header files and uses it to generate internal fixes. This is part of fix includes, something that I had alluded to earlier. Normally, fix includes isn't needed on a system running with glibc, but something about my cross-compiled system was unhappy when loading various system headers with this directory removed. So I put it back and took a closer look. What I found is that in its current state, GCC could build simple programs, which is what let me build Hello World, but more complex ones had problems. I got this frankly fantastic error message from diffutils complaining that it only worked on systems that supported 2 complements math, which is all modern PCs. Much to my horror, I had found that several InterX headers, complete with Microsoft copyright, had ended up on my Linux system and were being used in place of Linux or glibc ones. I spent some time debugging it, but this 8-hour stream was coming to an end, so I called it there and picked it up later. The following day though, I was right back at it. Through some careful debugging, I realized that what had happened is that instead of generating internal header files like we did for stdint back on InterX, the cross-compiled compiler had simply copied them from InterX directly. This represented a somewhat prickly issue since while I was begrudgingly willing to make an exception for Pixie Linux, GCC was a bridge too far. Removing the fixed includes folder caused the compiler to break in other ways. A deeper dive though revealed that this ultimately boiled down to one thing: limits.h. Limits.h defines various limits for things like variable sizes and such. glibc does provide its own copy of its header, but it was then trying to reference GCC's internal copy of this via the include next directive. However, this reference is only used when glibc is used with GCC and has a fallback mechanism on core limits. So on a hunch, I commented out the if-def guards and the include next statement, which actually seemed to fix things. Or, well, at least I was able to build parts of diff utilities. The top-level makefile was still unhappy for reasons that were unclear. However, I suspected the actual root cause was actually the fact that I was currently using bash as an int system. This normally is only done as a last resort when the system is capable of nothing else. One of the side effects of this is that I didn't have job control, meaning that neither Control-C nor Control-Z worked to interrupt or suspend processes. I also suspected it would cause problems with make, which spawns subshells and does various processing tasks, which were no doubt breaking. So the next goal was getting the system up multi-user, or at least as close as I could get. I chose to use system5int because cross-compiling systemd seemed like pain and got to work. This required building eudev, shadow, and a handful of other packages required to allow user accounts and such to work. It also required a lot of hand-holding, and I ended up skipping a few packages that, strictly speaking, weren't 100% necessary. It wasn't hard, but it was long and slow. Eventually, I got enough built that I was ready to make the attempt. I removed the int bin bash option from the kernel boot flags, rebooted the VM, and waited. Sure enough, after a bit of a wait, I ended up at a login prompt showing that int had started and enough of the system was working to spawn consoles. That would have been a major win if I could log in. I hadn't set a root password, so I quickly rebooted to single user mode to do so, just to find out that my cross-compiled copy of password didn't actually work. I could manually set the shadow password, but before doing that I had a hunch. Well, it doesn't seem like there's much difference between starting bash as int and booting into single user mode. The latter does actually set up a full console, and more importantly, since bash isn't PID1, job control started working. What didn't start working was diffutil's makefile. I spent some time looking at it in an editor and determined that it was falling over with pathing issues in relation to shell scripts, which was strange to me. However, I had a theory. I had stated earlier that unless a lot of special work is done, configure scripts have to make guesses when cross-compiling. I already knew my cross-compiled bash would have problems with some test suites, but now I was wondering if there were deeper gremlins. So with nothing to lose, I copied the bash source code into the NFS root and tried to build it. Configure ran just fine, as did make, which was a nice change of pace. It did show that I was now capable of building non-trivial pieces of software. However, there was something else. This was fast. Very fast. Throughout this entire project, I had to deal with XP being very slow. Quite a few people in chat kept telling me that the problem was with Hyper-V or disk drivers, but I knew from experience that XP was just very slow when it came with dealing with fork and process spawning. Here now though, I am running a Linux kernel with a userland hosted off XP's NFS server, and it was fast. Not as fast as a native system, but a literal order of magnitude better than what I had been dealing with. It showed that the problem is that while services for Unix is faster than Cygwin, it's still not performant, and this is the proof. After all, the file I/O was still going through XP, so if there was a driver or deeper issue with NTFS, it would show up here. It's nice to know that you're right and then proving it. Bash finished not long after, and I even ran its test suite right after. It had some test failures, largely relating to locales, but it seemed happy enough. The question was, though, would it fix my build issue with diffutils? Yes it did. After installing the new bash, diffutils built without issue, showing the problem was in fact the choices configure had made while cross-compiling. That was progress. Now what followed was the rebuild broken things natively part of the stream. This started with core utilities since I already knew I was missing a df command, and followed through with util Linux and Shadow in an effort to get a system I could actually log into. After rebuilding Shadow, I did get prompts to set a root password, but it was erroring out complaining that it couldn't log the password database. This was no doubt Microsoft's NFS server at fault though. Furthermore, I had gone fdisk from util Linux, and after building E2FS progs, I was able to partition the hard drive, format the boot and root file systems, and copy everything over. I was also able to chroot into my just copied file system and set a root password. However, I wasn't quite ready to boot off it just yet. The biggest issue is that when netbooting, the Linux kernel can mount an NFS share for you to use as a root file system. However, to do that on a running system, you actually need a fairly large collection of programs to get the mount.nfs command. You also need a way of configuring the IP address and do DHCP configuration. I did start building these, but the amount of copying files, building them, and installing them was starting to get to me, so I looked for something simpler. That simpler thing ended up being Lynx, a text mode web browser, which could connect to the same Python-based web server that I've been using to copy files into the Windows XP VM. This was a nice quality of life feature, and I also built Perl and OpenSSL to go along with it, since I was going to need to build the Linux kernel soon, and I wasn't going to compromise by turning off feature flags this time around. I should have built a DHCP client as well, but it's actually possible to tell the kernel to configure an interface at boot time via DHCP with the IP equal DHCP switch, and that interface will stay configured into the running system. With Lynx and my very janky network setup, I started working towards building the kernel. First up was upgrading GCC to 8.5, which went well enough, although I also had to update bin utilities before it would build. After that, I took the kernel source tree, grabbed the default config, enabled the Hyper-V options I needed, and built it. Once that was done, I just needed one thing: grub. After copying grub over, it was a simple matter of building it and installing it to the master boot record of my Linux VM. Then I could just copy the just built BZ image, set up grub.config, and I was done. I had accomplished everything I had said I was going to do and built Linux from scratch from Windows XP. I proved the system could self-host, which was the stopping point I had set out earlier. But it seemed a tad anticlimactic, and a lot in chat were disappointed that I wasn't going to build a desktop environment. And honestly, so was I, but I was hesitant to commit to another 20 hours of work. Furthermore, while my system was functional, it was a hodgepodge of different versions and such. But what if there was a way I could build the rest automatically? Turns out there's automated Linux from scratch, which does exactly that. It's not well documented, but it essentially runs every command from the LFS book and builds a system from that. It also supports building beyond Linux from scratch packages, which handles everything like desktop environments, web browsers, and more. It would still take hours to build, but this was, on paper, a way to set it and forget it. Also, it is effectively just Gen 2 with extra steps, but we'll just ignore that part. Actually getting ALFS running was a bit more effort. It had a couple of dependencies I needed to tackle, and I needed to be able to download files from encrypted websites. This on paper was simple enough, although actually loading the certificate store proved to be a giant headache. Turns out you need devstdin, which itself is a link to a file in the proc file system. I assume the main reason I lacked this was due to my absolutely ancient version of EUDev. But after a bit of legwork, I got it working and it started rebuilding the base LFS system. A few hours later, it was done and I was ready to move on to the next step. In theory, ALFS should have also been able to install the tools to run itself, but this kept erroring out. Undeterred, I carried forward. I booted the system back under the XP NFS root and moved the bootstrap system to a scratch folder, and then moved the just built LFS system into the root directory, effectively replacing everything I've done with a consistent baseline. After some fiddling, I was able to log in and carry on. After that, I also installed DHCP-CD because I got sick with fiddling with the network by hand, and then reinstalled all of ALF's tools so it could run. After which, I told it to build the BLFS tools prefix and could start selecting additional software to install. I had a few false starts here, but after figuring out how to get the tool running, I told it to build Xorg and then XFCE, and let it run while I wrote this script. It had some problems with dependency order, but as this is a bonus end to the video, I'm just going to say that I got it built over the course of a day with only having to occasionally tweak it. That's what I call progress. Actually starring X was an entirely different bundle of pain, as in several hours of debugging, which kinda made me regret doing this, but whatever, it's done. To make a long story short, I had to figure out the kernel DRM options, decrypt Xorg's confusing error messages, manually track down the fbdev driver for Xorg, compile it, and then and only then did I get XFCE to load. Also, my mouse was screwed up and operating back to front, but who cares? So, that's it. It's done. Linux, successfully bootstrapped from XP, built to the point it can self-host and more. I have a bit more to say, but if you've enjoyed this content, consider liking, subscribing, or becoming a member. I'd like to hit 50k subscribers this year, so every bit helps. Now for an afterword. This video represents a turning point for the channel. As I stated in the beginning, this change in format was an experiment in how I make content, and well, I think it was successful. For those new to the channel, I've been uploading the individual parts of this video as separate dev vlogs as I finish them to members and Patreons as soon as they've been finished, and then releasing the final product all at once it's done. In terms of total time, this is likely taking more time overall than just doing a project and editing it, but each individual step was easier to get out the door, and I'm happier with the final product than I've been with several of my previous videos. So I'm calling this a win, but there's a bit more. One thing you probably won't see going forward is a lot of real hardware, and that's mostly because my life behind the camera has been, shall we say, a bit chaotic. I've moved not once, but twice from New Jersey to Portland, Oregon, and then again to Greece. As part of this, I was forced to divest my collection of vintage hardware and more. I didn't just throw things out, but I did find new homes for everything I had, which was a time-consuming process to say the least. To say there's a story here is, quite frankly, understating it, but it's not one I'm quite ready to share just yet. That will come with time, though. Aside from my desktop, laptop, and NAS, I've only kept my amateur radio gear as elements of my previous life. As such, most of my projects going forward are likely to be emulation of some form. I will also be looking at pivoting more out of vintage technology and onto more broader topics. One of those topics will be more on amateur radio and my various radio projects. Another one is going to be going more into depth in the history and depths of the internet, how it evolved, and how it got here. Finally, I also intend to write a book. I will no doubt livestream parts of the writing and research process while I do it. Along these lines, I've also made the decision to go back to school and am currently enrolled in distance learning classes from Open University, a UK university, and am studying politics, philosophy, and economics. It'll be a while before I finish that degree, but what I've learned thus far has already helped me understand many of the things that help explain why our world is the way it is. As a side effect of this, I've ended up cutting my life down to the bare minimum. In many ways, it's a return to how I lived in my 20s. In those days, I wandered the world living out of a backpack, waking up in foreign lands, and trying to find answers. I think now it's time to take what I've learned and start putting those lessons into words. If you want to support me on this journey, the links are down in the description below. I still feel like there's more I should say, but I think this is the stopping point. As always, this is your host and commander, wishing you a pleasant day and hoping to see you all again on the road of life. Until next time.